Hello, everyone. Welcome. Thank you so much for taking the time out of your day to join us for this exciting webinar. We're happy you're all here. As we let everyone join in, my name is Kayla. I'm representing the Acelab team here, and we have Brice here from H-Window who will be guiding us through today's presentation. So before we get started, let me show everyone very quickly where you can learn more about H-Window on Acelab. Alrighty, so hopefully everyone can see my screen. Maybe, okay, there we go. All right, so here we are on the Materials Hub homepage. So with the new updates, when you're searching for a manufacturer, just make sure that you type in the name and click manufacturer here so you can get the options. And this will take us to H-Windows page. So we've got quite a few things here for you to look over. We've got some basic information, Brice's contact info. We've got a video and quite a few products for you to explore. You are welcome to click into any of these products to learn more about it and save it to your firm library if you'd like for future reference. So yeah, definitely check out their page either during or after today's presentation. I'll drop a link in the chat for you to reference. Also got some case studies here as well. Yeah, so that's H-Windows page. A few other things to go over before I pass it over to Brice. Today's presentation is worth an AIA learning unit, so I want to make sure that everyone gets credit. So we did collect your numbers upon registration, so we'll use those. If you're concerned that we didn't get your AIA number, I will drop a form in the chat as well, so you can fill that out to ensure that you get credit for today's session. A couple other things, we do have Q&A available, so at any point during the presentation, if you'd like to ask a question, you can use the Q&A box at the bottom of your screen. And towards the end of the presentation, we will take some time to read out those questions. And we will also have a poll and a post-webinar survey for you to fill out as well. So that's everything from my end. Brice, back to you.
Well, hello, everybody. My name is Brice, and I'm excited to be bringing you this presentation today. Walls of glass have been a staple tool of architects wanting to express transparency and human aspiration, wanting to frame panoramic views and extend natural world into habitable space. But for far too long, those walls of glass have come with compromise. In addition to their poor thermal performance, conventional curtain walls have a limited material palette, resulting in mundane, lifeless, placeless, and cold facades. Timber curtain walls offer an alternative solution where high thermal performance meets authentic beauty and resource stewardship. Timber curtain walls can help you mediate the competing agendas architects are constantly navigating to strike a new balance for facade performance and design expression. So today, I'm going to be talking about timber curtain walls and how these can be useful design tools for you as you navigate the day-to-day work of an architect facing all these different competing agendas. So like Kayla said, my name is Brice Aarrestad. I'm the Director of Design for H-Window. I am an architect and have transitioned to the product side where I get to focus with H-Window on interacting with architects, helping drive collaboration as well as product development. So I'm excited to be sharing this product with you. It's one that we're thrilled to be part of. And what I'd like to do to start is talk about some content, configuration, design configuration, fabrication, thermal performance, carbon reduction, all of these different components that go into a timber curtain wall, but it's always good to start with a precedent project. So again, here's the chapters we'll be covering, but I want to start with a project. So this is the Rock Ridge High School. It's a project in Virginia, Minnesota, designed by Cunningham Design and DSGW. Virginia, Minnesota is up in what's called the Iron Range. So it's a northern part of Minnesota where there is a historic industry of mining, of timber, of all these different kind of resource extraction histories that are coming into now this new school project. So this was a high school that was designed to combine two different school districts into one new facility. So along with all of the design agendas that go along with the school, being forward focused in learning objectives, helping students feel warm and safe and comfortable, providing a lot of different space varieties for different educational activities. There was some additional design agenda put on the facade, put on the envelope of the building. So I've listed here just 3 of the pieces of agenda that they were trying to achieve. So expressing the regional character through the building materials, using expansive glass to enliven and attract students to these community spaces, and then investing in the envelope for reduced first costs and reduced annual costs. So I'm just going to click through a few different photos here. So expressing that regional character, they're using a timber curtain wall for these large glass openings. One of the things that was a driver for this project was trying to use high performance products to reduce the air infiltration of the envelope. They did a lot of testing and a lot of design calculating, and found that if they can make this envelope really, really tight, really airtight, they would be able to reduce the size of the mechanical system, which would allow them to offset the increasing envelope costs, first costs, but also have reduced annual costs. So they're investing in the envelope to try to make their building very efficient, and thereby being able to spend money on architectural systems, on building features rather than on mechanical systems. So how do they do? For our work on this project, they were selecting a timber curtain wall primarily for these very large openings that you're seeing on the screen here. They needed these large openings to support their educational goals in the space. And they were limited in what they could do with traditional systems, and looked to the high performance timber curtain wall to help. So when it comes to air infiltration, on this project, buildings that have kind of high performance buildings typically have about a 10% higher cost than conventional buildings. This was a stat that their construction manager was able to put a measurement to. And then as a design team, they worked to find super hyper focus on this reduced air infiltration. And the results kind of speak for themselves. The code maximum of cubic feet per minute of square footage of envelope space is not to have 0.4, not to exceed 0.4. In this product, we have a really high performance value on air infiltration. And along with the entire envelope and the entire construction process, and making sure that any penetration through that envelope is sealed and protected, the actual air infiltration was 0.022, which is an incredible achievement, design achievement. And it was, a deep collaboration between product suppliers and selection, a deep collaboration between the construction manager and the construction processes, making sure that this was a really tight envelope. And one of the things that I thought was interesting, and they did blower door testing to understand these metrics. When the testing company came in, they set up all their tests. They kind of calculated how many fans they would need, and they started running their test. And they were seeing the fans just were shutting down. They had calculated too many fans in their blower door test because the envelope was so high performance. So, and what does that do from an energy use standpoint? Transitioning from air infiltration to energy use, a baseline building, so a typical building, school building like this, would have 55 kBTU per foot square per year. And then the actual performance of this building is 45. So there's about an 18% improvement in energy because of the focus and attention to their envelope. So before we go too far down, we should probably talk about the systems, talk about some of the configuration that is achievable with timber curtain wall, and how you might design a system for your next project. So I want to start with a piece of terminology. This is what we refer to as back members. Most curtain wall systems use an aluminum back member. This is the structural component that resists wind load, that holds the glass in place from a gravity standpoint. In a timber curtain wall, we replace what is traditionally this aluminum back member and use an engineered wood. I'll go into kind of how that wood is constructed and the requirements of that a little bit later in the presentation, but just want to throw that out there. Key piece of terminology there: back members as the structural components and the timber components in a timber curtain wall. So one of the early aspects of a project when it comes to consulting on a project, helping your design teams configure a system, is understanding the back member depth. And we get to that number by calculating the span height, the width between mullions, and then the wood species, the timber glulam species, along with the wind load. All of these different factors go into a calculation that help determine the depth of that span, that back member. Compared to aluminum systems, a timber curtain wall system can achieve really long spans. The span to depth ratio, like I said, is similar to an aluminum span to depth ratio without the reinforcing. As soon as you add steel reinforcement to an aluminum profile, its span to depth ratio is much better than a timber curtain wall. We're not able to introduce steel vertically into the mullions, so we don't have the flexibility of using shallower depth mullions with a steel reinforcement like you would with aluminum. But what we do have the ability to do is to tune the depth of that back member. So whereas aluminum system, you can have 4, 6, 8, 10-inch depths, we can really vary the system on a inch-by-inch increment, maybe even smaller than that, half-inch increments if needed. So it becomes a really unique tuned facade based on these structural spans. So that's kind of the initial understanding of the first part of a timber curtain wall system design. The next part is, what are the glazed-in panels? Similar to a conventional curtain wall, we can do operable windows, doors, mechanical vents, a lot of different glazing panel types: opaque panels, spandrel panels, glass of 2 and 3 panes. When looking at the depth of this system, how thick that glazing panel can be, whether it's an IGU, an insulated glass unit, or an aluminum sandwich panel, the depth can vary from 1/4 inch to 2.5 inch. We typically see a 1/4 inch panel on an interior application, whereas a thick 2.5 inch deep IGU is getting pretty hefty out there, but the system can handle that, can support it. Another thing I think that is really interesting is when you look at traditional curtain walls, there's a range. You can go from the hyper kind of off the shelf, these are just components that we just plug and play, all the way to the other end of the spectrum. That's a super bespoke custom curtain wall where every little connection is a unique design element. And what I like to think of the timber curtain wall being is somewhere in between. You're able to do a lot of unique customizations with it that you can't do with an traditional aluminum system, but it's not so unique and so custom that you don't have these kind of off-the-shelf ready pieces. So what I like to do is I like to call it the hot rod facade. So, thinking of a hot rod, you take a standard vehicle and you switch out the tires, you put in a flashy spoiler, you add some paint, you make it a hot rod. This is a system that allows you to do very similar things. So vast customizations are possible and often easy to implement. I want to dive into another precedent project here that kind of shows how this hot rod facade really works. So this is a school in Saugus, Massachusetts. designed by HMFH Architects. And their design agenda, again, it's a public school project. So in addition to all of the educational features, on the envelope, they were looking for daylight optimization in a lot of their kind of shared community spaces. And then with that, they were looking to reduce glare. Having a lot of expansive daylight comes with the challenge of glare. So they're looking to reduce the glare. One of the ways they did that is through the use of these interior light shelves. So, and this is in their library and media center. So it looks like a really hyper bespoke, custom curtain wall, but it's really a pretty simple kit of parts. So you have the timber curtain wall that's doing all of the typical things a curtain wall would do. But then we also added these shelf pegs. So, you can do things with wood that you can't do with aluminum. So we would install these shelf pegs, and then the horizontal members there are just set into place, literally like shelves. This project was also done using laminated bamboo as the back member, as well as for the shelves. And so uniform materiality was another design aspect on this project. They used laminated bamboo throughout the school on fixtures like built-in benches, on wall panels, interior wall panels, window surrounds, things like that. And they were able to achieve that kind of uniform materiality throughout the project, tying in the curtain wall to these kind of finishes, allowing that to be a really seamless experience. And it felt, coming through the school, it feels like you're in a furniture piece rather than in a building. Some other components on the hot rod facade that are unique to a timber curtain wall is some of these accessories and integrations, using a knife plate that would penetrate through the glazing assembly and connect into the glulam timber, minimizes a lot of the thermal bridging that occurs with some of these connections, and allows you to do other things on the exterior, which could be sunshades, PV panels, canopies, things like that. Either through these knife plates or through sockets and hooks and different attachment pieces that can be integrated. So we're starting to get down the road on components, fabrication, and installation. So I think what's really interesting with these curtain walls is to understand how they're built so that you can understand how best to design them, and really maximize the ability of the different components and components that can work together to provide a really unique system. There are kind of two different types of curtain walls. The first one that's more typical is the captured curtain wall, and the other one is a structural silicone glazing. So in the first one, you're using a mechanical attachment to make sure that the glaze panel is held in place. So you're using a pressure plate that is screwed into that back member, clamping the system together. The structural silicone uses an adhesive to adhere the back member to the glass, or the opposite way. So two different ways of building a curtain wall. And what I want to do is first start with the captured glazing, the different components and aspects of that. And then I'll follow up with the silicone glazing. So we'll start with the component parts of the captured system. In general, you have the timber back member, the structural anchors, timber connectors, base profile, interior gasket, glaze panels, and then the cover assembly. So I'm going to walk you through what these look like in person here. I've got a couple samples that we can look at. The first one here is, like I said, it's a typical captured system. You're seeing the profile of the mullion here. We use just some acrylic blocks to mimic an IGU. We're not generally installing thick pieces of acrylic in an envelope, but this is just to demonstrate the product a little bit. We'll start on the interior and work our way backwards. When it comes to the glulam, the timber part, we can do a lot of different things with it. There's different wood species that we can use. different wood species include Doug fir, southern yellow pine as kind of some softwoods. We can do some hardwoods like white oak, maple, ash, all sorts of different species there. The sample that I'm showing you here is a bamboo, so laminated bamboo, like I showed on that Saugus project. And what I think is unique about these systems, or one thing to keep in mind, is that when it comes to any sort of curtain wall and any sort of material that is supposed to be bracing against the wind, you want to know how each of those components in that system function and how they'll perform given wind loads, given gravity loads, and other loads that might be attached to this system. So we can't use, just heavy timbers because they twist, they move, they crack, they separate. We can't use stock 2x4s or 2x materials. We have to use an engineered wood. So most times it's a glulam. And what I think is interesting about glulam, the process, is how controlled it is. Throughout the entire fabrication of that glulam assembly, they're monitoring the temperature and humidity in their factory. They're making sure that they're doing periodic adhesion testing to result with a timber that has a lot of known quantities. You know how it's going to perform over time. So going back here to our timber our back member, we can do this, like I said, in a lot of different species. Bamboo, I'll talk about that in a little bit here. But just know that this is a species, or this is a material that is highly engineered and will not perform as you would think of like a 2x material. So as far as expansion and contraction, it's very minimal. We're able to ensure that any of the kind of material limitations of timber are controlled. The next piece I want to talk about is the bamboo. So bamboo back members, we use a species that comes from Asia. It is a rapidly renewable material. It surpasses engineered wood in both its sustainability as well as its dimensional stability. It's manufactured by cutting the bamboo stalks longitudinally in strips, planing them flat, adhering glue, and then compressing them into kind of a board form. The resulting product has a high degree of uniformity and consistency. While there are nearly 1,600 different bamboo species grown in tropical and neotropical climates, the bamboo species most prevalent in timber curtain walls is called maso, and is, like I said, sourced from Asia. Harvest time is about 7 years after cutting the previous harvest. So what I think is really cool about bamboo is this is a species, this maso species, can grow between 65 and 90 feet tall in that 7-year period. It actually grows that tall in a very short amount of time. So you could think of like in the first year after cutting, it's going to exceed probably 40 feet, maybe even further than that. But you can't harvest it yet. It takes a little bit of time for the culls to thicken up and harden into a material that's usable for curtain walls. So that's why we get the kind of 6 to 7 year harvest time period. The other thing that's interesting about the way bamboo grows is, and why it grows so quickly, is if you think of like nesting cups. If you stack those nesting cups, it grows really quickly, right? And that's kind of the way that bamboo is too. You take all these different rings, and each one of them is expanding at the same rate, but collectively they're expanding exponentially. So that's why it's such a rapidly renewable material and so useful for products like this. The next key component is the structural anchors. Oh, before I go into that, one more key piece of terminology is mullion and transom. So mullion is the vertical member, transom is the horizontal member, or if there's an angle, it's the angled member. Usually the mullion is the component that is doing all of the bracing against the wind loads. So the mullion is really the structural member bracing those wind loads, and the transom is the member that is holding up the gravity loads of the glazed panels. So mullions are vertical, transoms horizontal, but sometimes we call them horizontal mullions. But let's be technical here. So, all right, component parts. Back to structural anchors. There are a lot of different ways that we can connect this system to a timber curtain wall to a primary structure. You're seeing a lot of different connection types here on the screen, different anchors. What I think is important for you to understand is that each one of these projects typically has bespoke structural anchors. These are usually made out of steel. They can be configured in a lot of different ways to meet your project conditions, whether it's how you're anchoring to a knee wall, a concrete stem wall, how you're anchoring to a mid-span connection, whether that's a wind girt or whether it's a floor slab, whether it's a welded connection or a bolted connection. There's a lot of flexibility and customization in this part of a timber curtain wall system. I think another interesting thing about this is also taking into consideration deflection. So you're seeing on these details here a lot of slotted connections that allow for the floor level or allow for the head of the unit to deflect, to allow gravity to force that piece up and down without impacting the glazing or the curtain wall. So like again, I said, a lot of this is kind of customized per project. You know, we work with the structural engineer on the design team side and on the product development side to design each one of these connections, allow for the deflection that is being expected in the building, and make sure that these components are solidly attached to the building. If we, again, are kind of working our way from the inside out, the next component I want to talk about is the timber connectors. And maybe the best way to do this is to show you another demonstration here. This is a hidden fastener system. So what I've got on the screen here is, if you can consider this a mullion, this clip here is the male side, and it would be attached to the mullion in our factory. And then this here, so this would be the mullion, and then this piece here would be the transom. And on the end of the transom, we have routed it out and then attached another clip. So this clip enables this is kind of the female side, enables it to slide into the male side. And this is usually done from the back. So if I turn it around here, so if you're looking at it from the face of the curtain wall, it slides in from the back to the front. So this would be the back side there. It's a hidden connection on the back. On the front side, it's going to get glazed over anyway, so you won't see it. And then the way it's secured is using 2 nail screws. So these are just, get a focus here, maybe not. So 2 kind of bespoke screws that have a nail portion and then are finished with threads, and they slip into the joint and lock it together. So that becomes a really rigid joint. And it's, like I said, it's completely concealed from the inside. So that's the hidden joint timber connector. All of these components, like I said, are attached in the factory. So the mullions receive the male parts, the transoms receive the female parts, and they're attached in the factory. So all of the routing, all of the cutting, pre-assembly happens in the factory. The next component is the base profile. So like you would see on kind of typical aluminum systems, this is the T that you would see on those systems. So if I go back to my camera here, So this profile here is the base profile. It's continuous on both the transom and the mullion side. And this is what receives the screw that clamps the system together. That's called the base profile. Again, this is fabricated in our facility, cut to length, and pre-attached to the mullions and the transoms. On top of that, you have the interior gasket. So this is the interior sealant of the system. So looking at this one here, it's this black EPDM rubber, and it wraps over and around the base profile, creating a thermal break, but also creating an air barrier break. So you're having that kind of primary seal on the interior and or primary on the exterior and secondary on the interior, but the interior seal is pretty robust. There's a lot of different options for how these go together, or different profiles of these gaskets. It's maybe not as critical for you to understand which each one of these do. It's just ways that they are layered together that helps direct water out of the system. You know, like any window, any glazing product, there's always going to be water into the system, moisture in the system, and how you ventilate or extract that water is really key to the type of system it is and the performance overall. So you're seeing 4 different profiles here. Again, they're just different steps of kind of where these things can overlap. That one with the hook there, that would be a sill profile. So that flap is able to wrap, and you're able to use that to kind of flash through the system, and then it would be, you know, trimmed in the field to whatever length it needs to be, as far as its length out of the system, you know, flashing out of the system. All right, the next piece here is the glaze panel. So like I mentioned before, there's a lot of different things that we can do with this glaze panel. Double pane, triple pane, you know, all of the technology that you can do with glass, you can apply into a timber curtain wall, you know, whether that's electrochromic glazing, photovoltaic panels, mechanical vents, louvers, doors. There's a lot of different things that you can put into these framed openings. So the glaze panel. The last piece on kind of the glazing aspect here is the glass carrier. These are ABS clips that are attached to the transom, and these are really just there to hold up the glaze panel, typically an IGU. So it's not resting on the base profile, which would, in most cases, void the warranty of that glass. So these are, you know, custom, or not custom, but there are a lot of different varieties that we can do depending on the thickness of your glaze panel, and then the number of glass carriers required per panel is another thing that we calculate to make sure that all the gravity loads are carried. The next component I want to talk about is an insulation block, and this is a piece of foam that goes into the glazing cavity. And what I'll do is I'll show this on the screen here. I've got a big sample. This one's a little heavier, so let's try this one. A little heavier, but it's let's see, focus. Try focusing here. Maybe it's gonna go, maybe not. All right, well, we'll just have to keep it zoomed out then a little bit. Yeah, that works. All right, so it's this piece of foam here, and it's just filling in the cavity of this space between the base profile and the pressure plate. It's filling in that cavity. It's an accessory. You don't necessarily need it on every project, but it does have a thermal performance aspect that some people value, because it takes what would have been a point, let's say 0.17 U factor, and brings it down to a 0.16. So that's the insulation block. Now we start to get to the exterior components. So starting with the pressure profile gasket, and these are EPDM gaskets that are friction fit into the pressure profile. So this is the aluminum extrusion that is basically clamping the glaze panel into the back member using screws. So if we go back to our sample here, so if I take this off, so we're seeing it's the cover, or sorry, the capture profile, pressure profile, and then it's being screwed into the base profile. And then you finish that off with the cover cap. So the cover caps come in a variety of flavors. If we look here, we've got, got a lot of different ones on the screen here. These are being shown in millimeters, but different components based on kind of your design aesthetic. Typically, we would use a 15 millimeter thick cover cap on the verticals and a 12 millimeter cover cap on the horizontals, so that there's a little bit of a shadow line between the horizontal and the vertical, because when you, even on this sample here, using kind of a light bronze anodized sample, when you see the cut end of it, it has a kind of a bright aluminum appearance. And so when these are put together in the field, you want to kind of conceal that cut end. So that's why you would use a thinner or a thicker profile on the horizontals, and then the verticals would die, or the thicker profile on the verticals, and then the horizontals would die into that. The other thing I think is unique to this product is the ability to use wood cover caps. We generally only see this on an interior application. So like if you're doing a vestibule doors, you would have this on the interior so that you can have kind of a continuous mullion look to it. So these are attached using clips that are screwed from, it's going to be a little bit difficult to see it in the camera here, but clips that are screwed into the profile of the wood, and then those clips snap into the cover profile, which you're seeing. This cover profile or pressure profile is a little bit different from the other version. It has these two clips that allow it to grab onto that wood profile clip. So like I said, this one is bamboo, and you know, as you would expect, any natural material on the exterior of a building is going to be subject to maintenance. So there's different, you know, finishes and options like that you can do to extend the life, but it would be something that would need to be maintained over time. What I think is unique about this system, though, is that since it is a cover cap, you can literally remove it. I'm not going to do it on this one, but you can remove the cap. The gaskets are friction fit, so you don't even need to tape those off if you were going to refinish the cap. So it's something that you could remove it. You're not having to deglaze the system. You're not having to tape it off. So you can refinish it in a factory if you wanted to, or offsite, and then come back and snap it back into place. So the next thing I think would be good to show you is how SSG components work. The system is, we're able to do it as kind of a standard silicone glazed, where you really do have the glass adhered into the back member, using some modifications to the profile gasket. But I want to show you the toggle option here. So this is our preferred method for doing structural glazing. And here I'll show you the sample. It uses what's called a toggle system. So in the IGU, in the spacers of the IGU, there is a toggle, so a channel that's put into that spacer, and then these toggle clips are rotated to grab that channel and then mechanically attached into the base profile. So it's kind of a hybrid system. Oh, and then it's finished off with a rain screen sealant on the perimeter. So it's kind of a hybrid system between a mechanical system and an adhered system. It's mechanically attached, but it's silicone finished. A couple more details I'll show you on the slides here. Might be interesting to see. So again, kind of a diagrammatic showing how, oh, that's not, there we go. Showing how the component twists into place. There is a, here it is in section. There also is a, and we're seeing it here, there's a foam gasket that fits into the glazing channel that acts kind of like a backer rod for that perimeter sealant. It provides a little bit of thermal isolation as well. And then here's how all of that works together. So that's how SSGs are usually accomplished. The other way that is an option too is to take a channel, a toggle channel, and adhere it on the inside of an IGU. So you would basically take this component here in the spacer of the IGU and put it on the inside, and then toggle that into the base profile. So you're in that approach, you're not having to get a custom spacer in your IGU. You're able to take that channel, apply any type of IGU that can be siliconed to that channel, and then mechanically attaching that, and then finishing it with your sealant, rain screen sealant. All right, so that was a long list of the components that go into it. I think one of the interesting things that maybe I missed with talking through this was the importance of having some space on the backside of your assembly, so that I pull these screws out here, so that, like I said, you can attach the system from the back to the front. So needing a little bit of clearance between the back member here, and if you have structure, if you have a column, if you have a wind girt, being able to fit that member between there. One of the things that is also unique is the ability to have different size mullions and transoms. So these ones are about 4 inches. Typically the mullions would be thicker than that. We can have all of these be the same depth, but you can also vary the depth for the horizontals. So oftentimes we'll see, if the back member is, let's say, 10 inches deep, you'll still use a 4-inch intermediary or horizontal transom. So some options there. When it comes to economizing the system, reducing the amount of timber is the key. So if we can reduce the number of connections, if we can reduce the depth of the system, that will save money over time. The next component or content we'll talk about here is the shipping and the way these get set up in the field. So everything comes from the factory labeled, packaged, palletized. You're seeing this pallet here that has, these look like they're transoms. The ends have the timber connectors already installed. Everything is cut to length. The gaskets, it may be a little difficult to tell from this photo, but if you look on top of the blue wrap, has the EPDM interior gaskets are pre-cut, preset, so that they can be put up in the field really quickly. We've had glazing contractors who said, compared to traditional aluminum systems, these timber curtain walls, since there is so much pre-manufactured and everything is really going together like a kit of parts, it can save up to 25% on field labor. So how do you install it? Like a conventional curtain wall, you're preparing the opening, wrapping, flashing, you're then setting your structural anchors. and then installing the back members. After that, it's setting the glass. So installing the back members, installing the horizontals, and setting the glass, sealing the perimeter, and then attaching cover caps. So it really does go together like a kit of parts, like a kit of Legos almost. In many scenarios after that comes field testing. So there are two different types of field testing that are often put together under one testing category, AMA 503-14. One of them is testing for air infiltration, and the other one is testing for water penetration. So they come out with an airplane propeller and spray water and air at it and see if it leaks. All right, chapter 3 here, thermal performance of timber curtain walls. Architects and building owners choose timber curtain walls for their natural beauty as part of a carbon reduction strategy and for their thermal performance. I think what's really interesting is when you look at all of the things inside a building that use energy, including the building itself. You've got office equipment, heating, refrigerating, cooking, cooling, lighting, ventilation. Think of that as an entire pie of energy being consumed in a building. 62% of that pie is influenced by the facade. The facade's influence on the cooling loads, the lighting loads, ventilation, and space heating. 62% is an incredible amount of importance put on a facade for its performance. So if you're looking to conserve energy in buildings, facade performance is vital. So how do you determine glazing system requirements? There's 3 general categories. It could be client expectations. Maybe they are trying to achieve certain building standards. Maybe it's building codes, so code requirements, whether that's kind of a standard code required U factor, or if it's a stretch code. Building codes oftentimes are helping to determine glazing system requirements. Another aspect could be mechanical systems. Like we saw on the Rock Ridge project, having a high performance envelope was able then to have a reduced mechanical system. So generally a variety of reasons that people choose one system over another based on their glazing system requirements. So when we look at thermal performance, we're really looking at 3, maybe 4 major components to look at. Number 1 is U factor. So U factor is the non-solar heat transferred through materials. If we're comparing timber curtain walls to kind of traditional aluminum curtain walls, a 2-pane system is between 0.29 and 0.30. A 3-pane system is 0.16 to 0.17, again, depending on if you have that insulation bar in your glazing pocket. Whereas aluminum systems are higher than that, 34 to 44 U factor on double pane and 20 to 22. So why is U factor important? We look at the thermal performance of a building. A window or any glazed product with a U factor of 0.36, comparing that to a U factor of 0.16. The wall's performance at 0.36 will be about 12% of its thermal performance if it didn't have the window at all. So, if it was 100% efficient, it would be the same as an opaque assembly, right? If you increase the U factor, or improve the U factor, I should say, from 0.36 to 0.26, that jumps to 27% efficient. So what is the difference between 0.36 and 0.16 when it comes to actually building a system? You're probably using a thermally broken curtain wall, and you're probably using a triple pane or high performance double pane system to get to that. So what we're seeing here is, again, you're kind of seeing these different lines. These are each window to wall ratios. And I'm really highlighting here when you have 70% window and 30% wall, how important is that U factor? So again, U at 0.36 is 12% efficient. U at 0.16 is 27% efficient. So that's a major increase in performance comparatively. So the next aspect of thermal performance we'll talk about is air infiltration. And again, I talked about this with the Rock Ridge project, but a timber curtain wall can achieve less than 0.06 cubic feet per minute per foot square at a pressurized 6.2 pounds per square foot. Aluminum curtain walls can perform similarly, but generally on the kind of upper end of that scale. So, and this is kind of pulling information from a variety of kind of your typical curtain wall manufacturing companies. The third aspect here of looking at thermal performance is condensation resistance. So condensation is important to resist because if condensation is forming on an assembly, it's causing moisture somewhere in your system to propagate and could lead to failure of other components within your wall assembly. So trying to reduce condensation just makes your building last longer. So what I think is interesting about how we test for this condensation resistance factor is this definition I have written here: condensation where an objectionable amount of conditions where an objectionable amount of condensation may form. So somebody was able to measure what's objectionable condensation and create a test for it. So not exactly sure how they came up with it, but they did, and it's the standard that everybody's using. And what we're seeing comparing timber curtain wall and aluminum curtain wall is if you're testing the condensation resistance of just the frame for curtain wall, it's at 98. 100% would be, or 100 would be completely resistant to condensation, right? I do have to add those numbers below it though, because what they found in the testing is that the glass, the glazing system or components are what are the weakest in that system from a condensation standpoint. So if you're using a triple pane IGU, that glass would have an overall system performance of 81. So again, the mullions, the transoms are higher performing than the glass when it comes to condensation. And then comparing that to aluminum at 68 to 84% from double pane to triple pane, there's quite a sizable change there. One tool that might be useful for you is the FGIA. This is the Fenestration Glazing Institute of America. They have a condensation resistance factor tool that you can access on their website, where you put in your project's location and mechanical system settings, a few other pieces of the form to fill out, and then it will calculate what your project minimum CRF value should be. So pretty easy to use tool and accessible to everybody for free. So the one final aspect on thermal performance is the discussion of thermal bridging. So we're seeing here an isothermal diagram based on finite element analysis showing reduced thermal bridging on the timber curtain wall compared to a standard aluminum curtain wall. And you'll note that on the aluminum back member, it's nearly 9 degrees colder. So when it's 2.5 degrees outside, 69 degrees inside, that aluminum mullion is almost 9 degrees colder than room temperature. And you're going to feel that. That's going to impact your comfort if you're standing right next to that aluminum, or if you have a desk right next to that aluminum, you're going to feel your energy leave your body as you're standing near that. Whereas the timber curtain wall, the back of that is white color because it's at equilibrium with room temperature. So again, we saw that on kind of the condensation resistance slide, where the mullion itself was performing better than the glass when it comes to temperature gradient there. So thermal performance was obviously about kind of the ongoing energy and the ongoing carbon used in a building. And what I think is also good to talk about is kind of not just reducing energy consumption through the operational life of a product, but reducing embodied carbon in the architectural systems. So we're going to talk about embodied carbon a little bit, and then we'll continue into some responsible forestry as well. If we look at just the materials, just the materials by themselves. Aluminum emits almost 7 pounds of carbon per pound of material, whereas a glue laminated timber, if it's Doug fir or southern yellow pine, something like that, will sequester, it will absorb almost a pound of carbon per pound of material. Bamboo is even further, it's about 1.6 pounds of carbon absorbed by the material per pound of material being produced. So on this chart alone, you're seeing an incredible difference between aluminum and wood when it comes to performance of a carbon of a product. But we understand, there's other aluminum components in the system. We have the base profiles, we have the cover profiles. So we can't look at just these single materials. We have to look at it more holistically. We do not yet have an environmental product declaration. We're in the middle of working on one, but we've got some data on this from the University of Washington study showing a few different aspects of a life cycle assessment. So the global warming potential, showing here aluminum curtain wall versus steel curtain wall versus timber curtain wall, and the global warming potential is outsized for aluminum curtain wall. We go to the next aspect here, acidification. This is caused by emissions reacting with water in the atmosphere and elevating acid levels in soil and water. Aluminum has 6.5 times the acidification potential as a timber curtain wall and steel curtain wall. If we go to eutrophication, this occurs when nutrients are over-fertilized in soils and water, leading to excess biomass and affecting life in the ecosystem. Aluminum curtain walls, again, are about 6.5 times the eutrophication potential as other products, steel and timber curtain wall products. The next one here, last one on this life cycle assessment, is the human toxicity potential. Finally, we see timber kind of edge the others, but if we look at what those chemicals and processes are within each of these systems and how healthy they are, we see that timber curtain wall, again, is performing better than aluminum and better than steel. And I think the aspects of this human toxicity are, it's the same aluminum figures, it's just a lower quantity, but then it's also how the glue laminated timber is adherent. Are there formaldehydes in the glue? And a lot of our suppliers are using formaldehyde-free glue in their glue lam back members. But again, this is a study not on our system, but on a different system done in 2012. The other thing to talk about with all of this is responsible forestry practices. Window is a member of the FSC. We source our materials from FSC and SFI suppliers as required on projects. We keep that chain of custody active and ensure that we are adhering to best practices on manufacturing side, but making sure also that we're adhering to best practices on a climate side. So the last slide here, just want to show you that, hey, we would love to talk a bit about system consulting with you, structural sizing, anchoring, design details, constructability, thermal bridging, value engineering. There's a lot that we can offer on these systems and hope to connect with you. So didn't leave much time for questions, but maybe we'll have time for a few.
Yeah, I can run through a couple in the last minute that we have. But again, anything else that's remaining, we'll pass along these questions to you, Brice, so you can connect with folks afterwards and share more insight. But let's go ahead and jump in. First, we have, do you offer different cap systems, for example, aluminum and wood? And what other custom profiles for the caps are like larger extensions?
Yeah, we can do a lot of different things. We can do custom extrusions, different shapes, sizes. We've done a few projects, especially with bamboo, that have used a pretty extensive cap. So this one is, just maybe an inch yeah, probably about an inch deep. We've done some that are pretty deep. And then there's just special pin connections that we use to make sure that it's secured. But happy to customize it. Yep.
Great. Well, we are at times, I do want to be disrespectful of everyone's day and their time. So we'll go ahead and end it here. And again, we'll answer any other questions via email afterwards. Any final words, Brice?
No, I appreciate it. Please reach out. We'd be happy to work with you and help you.
Yeah. Thank you for a great presentation, and thank you everyone for joining today. We hope you have a great day.